Look at a falling raindrop. For us on Earth, rain is the ultimate symbol of life. It's familiar, calming, and essential. But in the grand scheme of the cosmos, Earth is the outlier. You may have heard of strange rains falling across our solar system and the wider universe. Today, we will follow the scientific clues to uncover the most unimaginable storms humanity could ever conceive. Across the universe, weather operates under rules that defy human comprehension. Out there, rain doesn't nourish life. It involves substances that would melt, crush, or dissolve a human observer instantly. We are talking about liquid iron, molten glass, and solid diamonds falling from the sky. But how do we even know this? We've never sent probes to most of these worlds. The secret lies in light. Using advanced spectroscopy, we can analyze starlight as it passes through an exoplanet's atmosphere. By reading the chemical fingerprints hidden in that light, we can accurately reconstruct the terrifying weather of alien worlds light years away without ever leaving our solar system. To understand alien weather, we must first understand the physics of phase changes. On Earth, our weather is dictated by the water cycle. Water transitions seamlessly between gas, liquid, and solid simply because our planet's specific temperature and atmospheric pressure allow it to. But what happens when you turn the dials to the extreme? When pressure is measured in millions of atmospheres and temperatures rival the surface of stars, the fundamental chemistry of matter shifts. Take iron, for example. On Earth, it's a solid building block of our infrastructure. But at 2,400 degrees Celsius, iron doesn't just melt, it vaporizes into a gas. If that gas hits a cooler pocket of air at, say, 1,500 degrees, it undergoes a phase change, condensing back into liquid droplets. Or consider carbon. Found floating as methane gas in the atmospheres of gas giants, a single lightning strike can fry this methane into pure carbon soot. As this soot falls deeper into the planet, crushing pressures exceeding 100 gigapascals force the carbon atoms to rearrange. It becomes graphite, and eventually solid diamond. Weather, it turns out, is just a matter of physics pushing chemistry to its absolute limits. We don't even have to look far to find these extremes. Let's start with our closest planetary neighbor, Venus. Often called Earth's evil twin, its atmosphere is a masterclass in a runaway greenhouse effect. Here, thick, suffocating clouds are composed entirely of sulphuric acid. As these highly corrosive droplets fall from the upper atmosphere, they plummet towards a surface baking at 470 degrees Celsius. But here's the terrifying twist. The surface is so unimaginably hot that the acid rain boils away and evaporates long before it ever touches the ground, a phenomenon known as Virga. It is an endless, vaporizing cycle of battery acid. Moving further out to the immense gravity wells of the gas giants, the pressures scale to unimaginable heights. Deep within the atmospheres of Jupiter and Saturn, it is raining diamonds. The process begins with massive lightning storms that turn atmospheric methane into soot. As it sinks 1,600 kilometers down, the pressure turns it into graphite. By the time it reaches 30,000 kilometers deep, it hardens into diamonds. But they don't stay solid forever. Near the planetary core, where temperatures exceed 30,000 degrees Celsius, these diamonds melt into a vast swirling sea of liquid carbon. But diamonds aren't the only precipitation hidden inside Saturn. Deeper down, under pressures millions of times greater than on Earth, hydrogen and helium, normally mixed with atmospheric gases, undergo a bizarre phase separation. The environment is so extreme that hydrogen becomes a liquid metal, and helium condenses into dense fluid droplets. These droplets fall as a torrential, planet-wide downpour of liquid helium through the metallic hydrogen mantle. This continuous friction generates massive amounts of thermal energy, which finally explains the decades-old mystery of why Saturn actually emits significantly more heat than it receives from the Sun. If you want a weather system that mirrors Earth, look to Saturn's largest moon, Titan. It has an atmospheric pressure of 1.5 bars, 50% thicker than Earth's. But with a surface temperature of negative 179 degrees Celsius, water is frozen harder than rock. Here, methane and ethane replace water. They form clouds, carve rivers, and fill massive lakes like Kraken Mare. Because of Titan's low gravity, the methane raindrops are 50% larger than Earth's, but they fall 6 times slower, like snowflakes. But don't let the gentle fall fool you. Intense Titan monsoons can dump over a foot of liquid methane in a single day. If Titan is eerily familiar, the worlds beyond our solar system are the stuff of nightmares. Welcome to WASP 76b, an exoplanet where the forecast calls for a 100% chance of liquid iron. This planet is tidally locked to its host star. The day side is permanently torched at 2,400 degrees Celsius, hot enough to vaporize metals, but the night side sits in eternal darkness at a cooler 1,500 degrees. This extreme temperature gradient creates ferocious winds reaching up to 18,000 kilometers per hour. These winds whip the vaporized iron from the day side into the dark night side. There, the sudden drop in temperature causes the iron to condense, falling from the sky as a relentless glowing rain of molten metal. But perhaps the most deceptive world we've discovered is HD 1897333b. From a distance, it looks like a peaceful, deep cobalt blue marble. It looks like an ocean world. It is not. That striking blue color comes from high-altitude clouds of silicate particles, essentially glass, that scatter blue light. But this glass doesn't just float. Caught in winds blowing at 8,700 kilometers per hour, 7 times the speed of sound, the molten glass rain doesn't fall down. It screams sideways around the planet. And to add to the horror, recent data from the James Webb Space Telescope reveals this atmosphere is laced with hydrogen sulfide, meaning this supersonic storm of horizontal glass also smells distinctly like rotten eggs. Why do we spend billions of dollars to study weather we will never experience? Because these extreme environments act as the ultimate physics laboratories. Observing these storms helps us understand how planets form and evolve. For instance, detecting heavy elements like barium, which is 2.5 times heavier than iron, floating high up in alien atmospheres, suggest violent internal planetary dynamics we completely missed in our previous models. And it's driving material science right here on Earth. Inspired by the diamond rain of gas giants, scientists at the SLAC National Accelerator Laboratory used high-powered lasers and plastic proxies to recreate the exact conditions of Neptune's atmosphere. They successfully created nanodiamonds in the lab. This breakthrough could revolutionize the mass production of industrial abrasives, medical delivery systems, and next-generation quantum sensors. As a species, we are obsessed with finding Earth-like worlds. But the truth is, the vast majority of the universe operates under physics we are only just beginning to simulate in our most advanced laboratories. Our quiet, watery weather is a rare, beautiful anomaly in a universe of violent extremes. So the next time you're caught in a storm and you feel a raindrop hit your face, remember, it could be a lot worse. It could be molten iron, or it could be glass, sideways.